for Japanese young scientists. And in this period of time, he also met Dr. Omar Yagi, with whom he started a long partnership that lasted until a few years ago. First at the University of Michigan, then the whole group moves to the University of California, Los Angeles, and after that, he moved to the University of California, Berkeley, where he has been. I mean, he was working with Omar until 2017, if my memory is correct, and then he moved to his current position at the as an industrial research coordinator in the group of Jeff Long at UC Berkeley, and he has been working there since then. But what I would like to say about Hiro, I mean, a couple of highlights that I actually liked it a lot, is that he was in 2015 he was named as one of the world's most influential scientific minds, according to Thomson's and Reuters, due to the number of citations that he received between 2003 and 2013. He has published more than almost 100 papers in international peer-reviewed scientific journals, and he has more than 30,000 scientific citations with an H index of 58. So I guess this a little bit speaks about his work. And he also was one of the main contributors to create the Global Science Institute, which is an initiative to help establishing world-class research labs in different countries such as Vietnam or Saudi Arabia. And it's my pleasure to introduce here to all of you. Dr. Furukawa has been also my mentor and friend for a long time. So I will give you the floor here so that you present your recent results. Thank you.
Yeah, thank you for kind introduction, Ali. Can you see my screen?
Not yet, Hiro.
Share.
There we go.
Okay. Yeah, thank you for kind introduction. I'm very happy to have some opportunity to give a talk. I actually wanted to visit Argentina because I like Argentina, visiting Argentina because it's a very beautiful country. But because of the pandemic, yeah, I don't have such opportunities this time. But anyway, today I'd like to talk about some hydrogen storage recent applications. So in 2016, US emitted about 5.3 gigatons of CO2, and yeah, this is a much greater, larger amount compared to the Argentina, about 0.2 gigatons. And in the global scale, we emit about 33 gigatons of CO2, and even under the COVID pandemic situation. So these CO2 emissions are mainly originated from fossil fuel combustion and mainly like electricity and transportation sectors. Also some part can be like industry or residential, commercial, or like agriculture. And perhaps, yeah, sorry. So question is, what can we do if we want to keep the global warming below 1 C? I mean, compared to the pre-industrial levels. And according to some Paris Agreement, we want to reduce the temperature like here. So in this case, perhaps one of the important strategies is capturing CO2 from point sources, because if we need to remove CO2 from some diluted atom, CO2 from atmosphere about like 420 ppm. So we need to process about 15% of Earth's air. So this is not really good strategy and realistic. So perhaps it's good way is try to use or replace some current energies using like renewable or nuclear, or use non-fossil fuel energy source for transportation like electricity or biofuels. And also some industry release a lot of CO2 like iron or steel production, cement. So if we can use some another energy source, perhaps it's easy or more realistic to reduce or remove these CO2 emissions. And under such circumstance, and in the US, early this year, some US Department of Energy, DOE, announced a new program called Hydrogen Shot toward net zero emission by 2050. So motivation is how to reduce the production cost, currently about $5 per kilogram. So, but if we are able to achieve some 80% of cost reduction, then perhaps a new market can be offered, including steel manufacturing, clean ammonia, or like also like we can use like heavy duty trucks. So DOE says $1 per 1 kilogram in 1 decade, one. But it is easy to imagine if we can make such opportunities or make some hydrogens for lower CO2 emission. So we need like next generation technologies that works, well for cheap production and also storage and transport. So we are considering if we can make some good compound to store hydrogens. So this slide summarizes the current portfolio of hydrogen storage options. So basically, physical-based storage and material-based storage. And these are, for example, examples of physical-based storage, like liquid or compressed gas, and cryo or cold compressed. So these three are more like matured technologies, but very low temperature or very high pressure is required. Also, geological storage can be proposed, but this is a very new idea, so nothing is actually proven. So materials-based storage are also studied recently. However, these are also long-term targets, but we could use like ammonia or methyl cyclohexane as a hydrogen carriers or hydrolyze or some adsorbent as a reversible hydrogen storage. So we are focusing on this new adsorbent. So MOFs are nanotubes. I believe you are familiar with the MOF synthesis, but if we are able to mix or find the right combination of organic linkers and some metal ion or metal cluster, we are able to make kind of extended frameworks. So many MOFs are very high surface area, having high surface area, and the pore environment is tunable. So, and some MOFs are very chemically stable, so it could be good for gas storage applications. Also, MOFs are used as like gas separations, batteries, or some catalyst, some variety of applications. And such recent work is introduced in the like recent chemical reviews. Actually, I draw this cover image using like single stroke illustration, although DOE didn't like and complained a lot. But if you have time, maybe you can just trace if this is really single stroke. Okay, so first, I just want to remind you, hydrogen storage capacity is commonly evaluated by hydrogen isotherm measurements. So this graph is a like hypothetical isotherm, and as you can see, if pressure increase, usually uptake also increase, and adsorption process is exothermic. So lower temperature gives us higher uptake, and higher temperature, if we increase the temperature, adsorbed hydrogen can be released. So because of this exothermic nature, using this type of equation, we are able to estimate some binding energy delta H, or maybe delta QST can be estimated. And important things to remember is lower operating limit of the tank pressure is about 5 bars, because usually engine inlet pressure or fuel cell inlet pressure is not 0 bars. So when we design new compound, we need to consider, how to minimize this uptake in the very low pressure range. So I quickly introduce how hydrogen research was developed. So first example of hydrogen storage is published in 2003, year 2003. And after this first examples, series of high surface area MOFs are prepared and analyzed by many groups. And this is one of the typical examples, like MOF2010 having high surface area, or MOF2021. These compounds are tested, and although at 77 Kelvin, these materials show very high uptake, and our total uptake in gravimetric unit is much higher than the DOE system target. However, these materials doesn't have high QST values, and 90%, 80-90% of pore is empty space. So volumetric density is very low, especially at the room temperature, and almost marginal improvement compared to the bulk density of hydrogen. So there's no point to use MOFs in practical sense. So community tried to improve the adsorption capacity using like functionalized MOFs or interpenetrating MOFs. However, it shows these models shows better uptake at low pressure range, but eventually doesn't really improve at high pressure range. So another solution appeared in 2005, like MOF505 is the first example to utilize the open metal sites MOF. And shortly after, other MOFs like HCAST1 or MOF74 system, these are extensively studied. So synthesis of MOFs with open metal sites are shown here. So if organic linker and some metal source are mixed, we are able to make like MOF74 structure, or maybe M2DOBDC. Then here, DMF is coordinated to each metal. However, if we are able to wash MOFs and heat the MOFs, then it is possible to remove this DMF without breaking structures. In this case, we are able to make coordinatively unsaturated metal sites. And as you can see, if we are able to enter this MOF pore, like about 14 angstroms in diameter, we're able to see this green open metal sites, and each metal distance is about 7 angstroms. So high density of open metal sites can be seen. So because of such high density of open metal sites, and when we took hydrogen isotherm at 77 and 87 Kelvin, the materials showed very steep hydrogen uptake like here. And once these open metal sites are occupied by hydrogen, then the material showed a very shallow uptake based on the physics option. And this trend is also seen by the QST trend. Once open metal sites is covered by hydrogen, then QST value drops. Then initial value is about 11 kilojoule per mole. This is quite high compared to the MOF 77 or MOF1, MOF5. So, however, problem is this QST measurement is more or less averaged information. So sometimes it's difficult to evaluate the site-specific information. So we use a IR system. So it's combined with like gas adsorption analyzer, cryostat, and IR spectrometer. So we are able to measure diffuse reflectance IR spectrum under this type of under like low temperature or very high pressure. So here's a typical example of IR chart, and it's also compared to the isotherm data. So when hydrogen gas is dosed to the samples, the absorption band like about 42 inverse centimeter appears, and this peak grows with increasing in the hydrogen pressure. And this peak position is completely shifted from the vibration frequency of hydrogen molecules in the gas phase. So degree of this shift indicates the strength of the interaction. And at the first stage, this site 1 starts filling and keep increasing the pressure. Second peak appears corresponding to the filling of a secondary binding site. Then if we continue dosing, then site 2 will be also almost saturated. And as shown in this like picture, pore is filled with hydrogen. Actually, this is a neutron diffraction data. So this also support like IR or isotherm data. So using this IR data, we are able to, from this absorption band area, we are able to estimate, make the Fund plot, Hoff plot, and from this plot, we can estimate the delta H or delta S values. And compared to this delta H site-specific value, the number is quite similar to the QST value that experimentally obtained. So question is, if is this in the optimal range of the binding energy? So this is a question. So to estimate the optimal binding energy or binding conditions, we can assume some simple Langmuir model, like there's a MOF, then put hydrogen, then hydrogen can be adsorbed. Using this simple model and assuming the Langmuir model, we are able to draw, write this type of equation. So this is actually theta surface coverage can be expressed as a pressure and delta G free energy functions. And in this case, surface coverage is plotted like at adsorption condition, room temperature and 100 bars. But we can do the same calculation like at 5 bar. This is a desorption condition. Then if we estimate the difference, we are able to get the usable capacity. And if usable capacity shows the maximum, so that can be the best or optimal delta G condition, not delta H. So in this case, about 7.7 is the optimal delta G values. And yeah, actually, this is a trade-off condition. And also, if delta G is higher or lower, then we can tune or control the affinity, like lower affinity or here's higher affinity. Then some groups like this Ariane group measured some enthalpy and enthalpy correlation for hydrogen adsorption, and we replotted this equation. And black one is some zeolite, and colored markers are MOFs. And actually, in the old study in 2006, the enthalpy value can be 8R. That was assumed, but in reality, if delta H increase, also delta S will increase. So it is very important to tune the delta G and delta G or delta H delta S. And according to this like figure, perhaps this blue area from like 15 to 25 of binding energy can be optimal. So MOF5 MOF74 shows like about 11 minus 11 kJ per mole of binding energy, but now we know this may not be good enough. So how to improve the or how to increase the binding energy? So one option was like increasing the charge density of the site. So we used something very similar organic linkers. I mean, just modifies the position of the OH group. So this meta DOBDC shows fortunately very similar MOF like with 1D per channel. And this compound shows a very steep hydrogen uptake in the low pressure range, very similar to MOF74. So this is a IR spectroscopy data. And then from the analysis, the binding energy was like 13.7. So this is even higher than one of the MOF74 type compound, like of nickel, were also cobalt. And the strong interaction was also proven by neutron diffraction. And actually, metal hydrogen distance is 2.18. This is very short. And actually, like this metal and hydrogen distance for MOF5, like no open metal site is about 3 angstroms. So this is good. So we prepared a large quantity of compounds and measured high pressure hydrogen isoforms and nickel to meta-DOBDC. This is one of the best compound among this meta-DOBDC system. It shows high storage capacity, and all isoform reveals greater capacity than compressed hydrogen at 25 degrees C. And if we use a minus 75 degrees C and 100 bars, the uptake is 24 grams per liter. So this is reasonably high. However, this is still short compared to the sort of DOE storage target. So perhaps traditional absorption is governed by like Lewis acidic mechanisms. Some weak polarization facilitates some binding of hydrogen or D2. So this may not be enough. So we thought maybe much stronger hydrogen binding mediated by orbital interaction could be important. So based on such ideas, we tried to make like vanadium MOFs. So originally we tried to prepare vanadium MOF74, but it was not successful. But using triazolate-based linker, we are able to make like vanadium BTDD type structure. And this is the crystal structure of the compound, and the local environment is something like that. Vanadium is coordinated with 3 triazolate terminal and 2 chloride. But in the real structure, I'm part of the vanadium site was oxidized, then capped by chloride. However, it shows a very high surface area like this, and the crystallinity is also extremely high. So here's the ambient temperature hydrogen isoforms. So we originally took 77 Kelvin hydrogen data. However, uptake is too steep, so we couldn't get the QST value. So we just measured the room temperature. Then estimated QST value from the hydrogen isoform is about 21. So this is what we want to get. And the uptake is much higher than one of the best compound for room temperature storage, nickel meta DOBDC. So IR data also consistent with gas absorption data. And again, we collected IR drift data, then make some plot, fun plot. So, and the peak position of this IR band is extremely large compared to like a nickel meta DOBDC or cobalt meta DOBDC. So traditional MOF is like 136, but here 242. And IR data also show a very similar binding energy. The important thing is the delta S value for vanadium MOF and the nickel MOF is very similar. So this leads to the very low delta G value, means so adsorption in like vanadium MOF is more favorable. So this is a good sign. And we also tested some crystal structure using neutron diffraction measurement. And this is a neutron diffraction data structure with no guest, no hydrogen. And CLVC angle here is about almost flat, means 175.8 degree. But once hydrogen or D2 is coordinated, so this angle is very small, I mean, getting small and very vented. So perhaps the bending on the hydrogen or D2 binding is to enhance the metal orbital overlap with D2. And the distance below 2 angstroms are much shorter than nickel and D2 interaction. This is 2.18 angstroms. So such idea is also proven by the theoretical calculations. So Martin Head Gordon group calculated, and they made some cluster model to vanadium and coordinated organic linker, just a triisolate part and some bridged chloride, and one of the sites is capped with chloride to imitate the actual structure. And by doing the energy decomposition analysis, I mean, frozen and polarization charge transfer term, I mean, we are able to split into 3 categories. And the important things is about 70% of total binding comes from like charge transfer. And the charge transfer component can be also divided into 2 parts. And the hydrogen sigma homo orbital to, I mean, charge transfer from hydrogen to like vanadium d orbital. Also, more importantly, some back bonding from vanadium site into this hydrogen sigma star orbital. So this contribution is a very large, and compared to like conventional MOFs, I mean, this is very large. So that's why vanadium MOF shows a stronger interaction compared to traditional MOF materials. And finally, we took high pressure hydrogen isotherms. So as you can see, like because of the strong interaction with the vanadium and hydrogen, we can see like strong uptake, steep uptake in the low pressure range, and especially lower temperature. And the uptake is much higher than bulk density of hydrogen. So this is good. However, the vanadium MOF doesn't have a very high metal density. So higher gravimetric uptake was achieved, but we still need to improve the volumetric uptake. So this research done based on the materials based, but we are also thinking some system level post analysis, because eventually we need to make some MOF pellets, pack in the like tank and transfer hydrogen. So in collaboration with the LBL like Brennig group, we performed the techno-economic analysis. And this is one of the examples of a techno-economic analysis. So, okay, so hydrogen can be produced somewhere, then transferred through the pipeline. Then hydrogen can be transferred to the city gate terminal. Then we use some truck to deliver to some each fuel station. So in this square, we consider the cost, and the end use for this study is like light duty vehicles. So as a reference, we also consider the cost. I mean, one kilometer, 50 kilometer means that how many, the distance we transfer some hydrogen. using trucks. So when we use a compressed hydrogen, 350 bars or liquid hydrogen, the cost is about $3 to $5 per kilogram. And we compare the cost with MOF5 or nickel metal DOBDC. It's state-of-the-art compound for room temperature storage. However, the price is extremely high. I mean, compared to like these systems, like 3 to 4 times higher. So this is because of the low storage density. So we need to use many trucks. And also, when we charge charge hydrogen into the MOF tank, we need to cool down the tank. So this costs a lot. So that's why, I mean, the price is not really competitive if we just use existing MOF materials. So we also tried some sensitivity analysis. And if we use extremely optimistic assumptions, for example, use driverless trucks or MOF cost is very cheap or two trips per day or something, then it is possible to reduce the cost like $7 or $8 per kilogram, although this is still higher than compressed compressed hydrogen or like liquid hydrogen. So perhaps increasing the volumetric capacity as a materials based should be extremely important. So in future, I mean, what we should do. So here I'm showing the future direction for the hydrogen research. So one of the directions is multiple hydrogen binding per metal sites. For example, manganese DSBDC, this compound is known, and the manganese site is one of the manganese sites are capped with 2-DMF. And if we can remove 2-DMF, there's a low coordination site. And actually, by neutron diffraction data, we we know, I mean, to hydrogen per metal can be possible to bind. So manganese doesn't show very strong binding energy, so this compound are not great, but we are now developing some chemistry to improve like these ideas. Also, another example can be like use of flexible MOFs, because when pressure is very low, the MOF shows the collapsed phase, means the hydrogen adsorption uptake is almost zero. But once pressure increases, pore expand and hydrogen can be stored. And this is experimentally shown only at like cryogenic conditions like 77 or 87. But if we are able to manipulate this phase transfer temperature or pressure, maybe this type of materials is very important. So we are working, but I'm hoping some young researchers in Argentina can also be my strong competitor, although I don't want to be upset. So here's the acknowledgement. So this work has been done with many collaborators. So I want to acknowledge like Jeff Long, also some materials prepared by Matt Kaprowski or David Romero, and IR measurement has been done, Henry, and some other people also helped me a lot. And Martin had Gordon group and Romit, they did some calculations, I mean, energy decomposition analysis. And LBL, Hannah, and Katerina, they did the TEA, techno-economic analysis. And NIST for neutron diffraction and NREL, I didn't show about temperature programmed desorption or some verification of desorption measurement, and these are done by NREL people. And finding, yeah, this this research is heavily supported by IMARC, I mean US DOE, so I want to acknowledge. And thank you for your kind attention. Maybe it's a bit rushed, but if you have any questions, I'm happy to answer. Thank you.
Thank you very much, Hiro. It was a wonderful talk, and we have a few questions. and we have a few minutes to address them if you're okay.
Sure.
So I will start just by a comment because I was surprised that the techno-economic analysis only accounts for the price of transporting the hydrogen, but I am sure that there is also an issue of safety, right? Of
Mhm.
course, it's cheaper to transport liquid hydrogen, but I would assume it's much less safer, right, to
Yeah.
transport. So, is there any value that you can use to compensate this, let's say, safety cost? And
Yeah.
that's
So
it. I'm sorry, go ahead.
yeah, go ahead.
No, I wanted to ask you a more technical design question, let's say, which
Yeah,
is
so
every
yeah,
time
this is
that,
actually a good
right,
question because eventually it's depending on the like DOT, Department of Transportation. So yeah, actually we got such questions from reviewers, but it was very difficult to address because we don't really know. But I believe like DOT can change the regulations if really we need to move to the like hydrogen economy. But for MOF transportation, we just set 100 bars storage, and this could be much safer compared to the like 350 or 700 bars storage or liquid hydrogen. But as you know, like some Toyota Mirai or some fuel cell car equips with like 700 bars gas tank, and it's relatively safe. So I'm hoping this won't be a big problem, and the government can find the well, resolution, solution to address these, your questions.
thank you. We also have a question from Matthias Rafti, another of the organizers for this symposium.
Mhm.
He's thanking you for your presentation and asking you if you could comment on possible issues raised by the liability against water exposure for the nickel DOBDC and regarding, for example, its application for hydrogen adsorption desorption. Uh, and also if can it be used for some kind of polymer coating, an alternative to improve the resistance to water, I guess.
Yeah, so yes, polymer coating is sometimes proposed, and I was aware of such papers. And for polymer coating, some CO2 capture people are considering because water contents in like CO2 capture process, like exhaust from like coal-fired plant, CO2 water concentration is much higher. And my understanding is there are some improvement. So, but I think hydrogen, for hydrogen purpose, water content is not really high. So if we just use like nickel metal DOBDC, water shouldn't be a big problem. And if necessary, maybe we are able to make some gold column. But vanadium morph is quite air sensitive, so honestly, I don't think it can be a real solution. But we are now making a different system, and the material also shows over 20 kilojoule per mole of binding energy. So that material may be another good solution.
Maybe you can present it in the next ArMOF.
Yeah, if you invite me, I'm happy.
Thank you very much, Hiro. It was a very nice talk, and thank you very much for your time and for presenting here in this symposium.
Thank you very much.
Okay, so we are going to move on and present our next speaker, who is Professor Martin Hartmann. Uh, Professor Hartmann